Today we're going to take a look at multiplicity. So let's go back first to our study of quadratics. Let's take a look at two functions. Let's say x squared minus 2x minus 3. Let's go with x squared minus 4x plus 4. If we find the roots, these factor nicely. We get x minus 3 and x plus 1. So we have roots at 3 and negative 1. 3, negative 1. So our parabola looks something like that. But for this guy, when we factor, we can see that what we have here is a double root. We get x equals 2 twice. Now this function will only make contact with the x-axis once at x equals 2. But what happens is the function makes contact, we intersect, and then bounce back the other way. Oh, that is the sloppiest looking parabola. Let's try that again. And that is g of x. So when we have a double root, we would say that it has a multiplicity of 2. And when there's a multiplicity of 2, our graph will intersect the x-axis, but not cross over to the other side. It'll bounce right back up again. But what happens if we have a multiplicity of 3? Well, we know a function, we'll call it h of x, equals x cubed. This function has one root at x equals 0, but a multiplicity of 3 because we would get 0 3 times here. And this is one of our common graphs, so we know that this goes like that. So here's our h of x. Here is our root of 0, but with a multiplicity of 3, instead of curving back up when we reach 0, notice that we cross to the other side, but there's a change in what we call concavity, where this section here is what we call concave up, but then it kind of twists and becomes concave down. So when we have a multiplicity of 3, we cross to the other side of the x-axis, but there's a change in concavity. So knowing all this helps us sketch functions. Let's say we're given a function that looks like this. First, what we can do is solve for the roots. So we set this equal to 0, factor, so here we're going to get a positive or negative 2. Here we're going to get a 0, except this will be a double root. So 0 has a multiplicity of 2 because of this x to the second power. So when we sketch this, we know that our graph has roots at positive and negative 2 and at 0. So now if we think about the leading coefficient test, we see that this has a degree of 4 and a negative leading coefficient, which means that our graph has to fall on the left and on the right. Now at positive and negative 2, we have a single root. So that means that our graph has to just pass through to the other side of the x-axis at plus or minus 2, but x equals 0 is a double root. So that means that we're going to intersect the x-axis, but not pass through, bounce back up, and create another local maximum there. And that is approximately what the graph of f of x looks like. Now let's try going the opposite direction where we're given the graph and we want to write the equation. Let's say that this graph is f of x. We can say that f of x has roots at -3, 0, and 4. But at -3 we would have a multiplicity of 2 because we intersect with the x-axis but don't pass through. We bounce back up here. At 0 we have a multiplicity of 1 because our graph just passes through to the other side of the x-axis. But at 4, even though our graph passes through, notice this change in concavity here. Here we're concave down and then concave up. So at 4 we must have a multiplicity of 3. So our factors would be, if x equals -3, the factor would be x plus 3. But with a multiplicity of 2, we need to square that. At x equals 0, we have 1, 0, so we would just have x. If you want to write x minus 0 in parentheses, that's fine. And then here we've got x minus 4 as a factor, but with a multiplicity of 3, that would have to be to the 3rd power.